So what if you could, seamlessly pattern conformal, nanoscale thin films onto incredibly complex 3D topographies? Like, imagine laying down metal nanowires over steep silicon slopes, or even directly integrating optical wire grid gratings onto the curved tip of an optical fiber.
Yeah, I mean, that is the ultimate dream for anyone listening who works with two-photon polymerization, or 2BP.
Yeah.
But historically, true 3D lithography just hits a wall when you actually try to pattern those highly functional conformal thin films.
Right. Exactly. So today, our mission in this deep dive is to unhack a recent Nature Communications paper that tackles that exact wall. It introduces a method called Scaffold-Architected Lift-Off, or SALO.
Plateau, yeah.
Yeah, and we're going to explore how this process leverages 2PP, not to print the final structure itself, but to print a highly engineered sacrificial mask, which is what actually unlocks true 3D lithography.
Well, to get to those dream applications you just mentioned, we first had to tackle the notorious conformal coating problem, especially with ALD, atomic layer deposition.
Because ALD is almost too good at its job, right?
Exactly. It coats every single microscopic crevice perfectly evenly. But that perfection is an absolute nightmare for traditional solvent-based lift-off processes.
Yeah.
The conformal coating just completely seals in your sacrificial resist.
Oh, so the solvent literally can't reach the sidewalls to dissolve it.
Right, the resist is just trapped in a shell.
Yeah.
But SALO gets around this by completely ditching the solvent approach.
Okay, so how does that work? You drop cast your standard IP dip photoresist onto your 3D target, print your scaffold via 2PP, and coat the entire thing with your thin film.
Yeah, and then instead of harsh solvents, you drop the sample into an ultrasonic bath filled with isopropanol.
Just standard IPA?
Just IPA.
Yeah.
It has low surface tension and low vapor pressure, and that creates stable cavitation during sonication. So you get these microscopic bubbles that collapse and generate highly localized microjets and shockwaves. Yeah, and this mechanical shear force is what physically snaps the scaffold off, bringing the unwanted thin film with it. Because it relies on mechanical shear rather than chemical solvent access, SALO successfully lifts off highly conformal ALD coatings.
Okay, let's unpack this. So instead of dissolving the mask, we're basically breaking it. It's less like an earthquake shaking the whole foundation and more like millions of microscopic power washers targeting deliberately weakened joints.
That is a great way to put it, yeah.
Blasting the scaffolding off without touching the delicate 3D substrate underneath?
Spot on. And the secret to that clean snap lies directly in the specific design rules you use when programming the laser path.
Like the geometry of the scaffold.
Exactly.
Yep.
For the cavitation microjets to actually break the scaffold, the height-to-width aspect ratio of the scaffold's attachment point has to be greater than 1.
Oh, I see. You need that geometric height to give the shockwaves actual mechanical leverage?
Precisely. Otherwise, it just won't snap.
Wait, but if I'm printing a standard IP-dip scaffold directly onto a polymer substrate, applying the laser is just going to cross-link them together? I mean, they'd permanently fuse, right? You couldn't snap that off cleanly.
They absolutely would fuse, which is why the paper outlines a really great workaround. For polymer substrates, you first deposit a 10 nanometer sputtered silicon dioxide layer.
Oh, so like a barrier layer.
Exactly. It acts as a diffusion barrier to stop the IP dip from covalently cross-linking to the base, ensuring the fracture happens cleanly right at the interface.
Okay, here's where it gets really interesting. Because even if we can cleanly snap this mask off, standard 2PP has a diffraction-limited resolution around, what, 200 nanometers?
Yeah, roughly 200.
But this paper is claiming sub-30 nanometer features. How are they breaking the physics of the laser?
Well, they aren't breaking physics, they're just using a brilliant processing trick. Before they coat the structure with the thin film, they expose the 2PP printed scaffold to an isotropic oxygen plasma.
Wait, and that physically shrinks it?
Yeah, it physically shrinks the polymer scaffold. So by shrinking the mask first, they successfully yielded patterned metal features as small as 27 nanometers.
So the oxygen plasma basically acts as a chemical shrink ray for the mask, cheating the diffraction limits entirely.
That's exactly what it does.
Okay, so shrinking the mask gets us down to 27 nanometers. But does this actually hold up when we try to build those dream applications we opened with?
It really does. They proved these concepts in the lab. They successfully patterned functional gold nanowires spanning 54.7 degree silicon slopes.
Oh, wow.
Yeah, and they also fabricated 1.5 micron line-width wire grid gratings directly on the curved tips of optical fibers.
No way.
And those gratings successfully diffracted 1550 nanometer infrared light.
That is incredible. So if you can now use 2PP to pattern materials using ALD or physical vapor deposition PVD onto any arbitrary 3D topography, well, what previously impossible 3D electronic or photonic device will you design tomorrow?